Hey, good afternoon. Welcome to this second online tutorial for Module 8, Basic Aerodynamics. This time I just want to go through a couple of other pointers really that may help you with your exam on Friday. Just some a little bit of information that people can often get a little bit confused with. One of the things initially in the atmosphere, when we're talking about different pressures and what's called the lapse rate, the temperature lapse rate, more precisely, is the lapse rate of the temperature. Now, take this as 2 degrees Celsius per 1,000 feet. I know in the book we precisely say it's 1.98, but remember there are no calculators in EASA exams, and so an approximate answer will be given on your multi-choice answers. So at 2 degrees Celsius per 1,000 feet, we should be able to work the actual questions out. Just be aware though that obviously once we get above the tropopause, it is then an isothermal region, which means that the temperature stays the same. So questions can come up depending on how many thousands of feet there are. Just remember, above 36,000 feet, just over 36,000 feet, the temperature will stay the same as the tropopause is an isothermal region. One other helpful hint which you could probably use is the lift formula and the drag formulas. Might be an idea just to write those down maybe on the question paper, unless they're already on the question paper as a question themselves, just so that when you actually are asked questions about lift, including density, velocity, surface area, you can look at the formula and decide on the correct answer, rather than just trying to think of it in your head. If you write it down, L equals, as we know, CL over half rho V squared S. If you write that down, and when questions come up about these particular parts of the lift equation, it can sometimes give you a bit of a helpful hint and enable you to answer the questions. As far as aerofoils go, we know there are symmetrical aerofoils and cambered aerofoils. One of the things to remember in a symmetrical aerofoil is that we know the chord line runs from the leading edge to the trailing edge, and the mean camber line is a line equidistant from the upper and lower surfaces. Therefore, on a symmetrical aerofoil, both the chord line and the mean camber line will be straight because of the symmetry of the aerofoil. Whereas on a cambered aerofoil, the mean camber line, the equidistant parts of the mean camber line will obviously be curved, whereas the chord line will obviously be straight. A cambered aerofoil as well will still produce lift, zero lift attitude at a negative angle of attack, due to the very symmetry of the aerofoil, whereas a symmetrical aerofoil will hit the junction of the CL and angle of attack point, the 0 point, exactly at 0 degrees angle of attack. So a cambered aerofoil will produce lift at a negative angle of attack due to the symmetry and the shape of the aerofoil itself. So looking into the lift and drag equations, just remember that most of these are V squared. So if we're going to increase or double lift, in effect, lift, drag, whatever else is going to quadruple at the same time. And obviously as we go higher in the air, density is reduced. So in order to maintain lift, something else has got to be increased. A lot of the time we're not necessarily going to increase the velocity. What we would increase, or what the pilot would increase, he could increase his angle of attack, which means his CL factor will increase in order to balance the lift equal to weight equation out as well. Induced drag, called lift dependent drag, only produced when lift is being produced due to the pressure differential between the lower and the upper wing. Have a look at an aircraft as such, a model of an aircraft. There's our particular one, so therefore we have low pressure here, or higher pressure than that on top of the wing, not higher than necessarily atmospheric. And air always travels from high pressure to low pressure. And so what will happen is we have a high pressure here and a low pressure here. Air will travel from root to tip on the lower surface, around the wingtip, and then from wingtip to root on the upper surface. So from root to wingtip on the lower surface, wingtip to root on the upper surface, because the air travels from a higher pressure to a lower pressure. Along with a chord-wise flow, obviously the relative airflow, as it goes over the chord, the two then meet up at the trailing edge of the aircraft, and this is what produces the vortices, the induced drag. And as we start to produce induced drag, there is a downwash produced, because as the vortex comes round, we get an upwash and then a downwash. This will then tilt the effective angle of attack of the airfoil rearwards, giving us induced drag. A couple of design features that can actually reduce the induced drag. Obviously, if we have air pressure flowing from the lower surface to the upper surface, we can either have an end plate on top of this, or more precisely, as you may know, we have winglets. They don't necessarily completely stop the vortices, but what they do is they separate the vortices out so that they stop them mixing at such a high rate, especially at the wingtip. Okay, so there's winglets as far as that for induced drag. And obviously another design feature is if we have a long thin wing, it reduces the amount or the strength of the vortices produced. So we have what's called aspect ratio, and that is a span divided by the chord length. So an aspect ratio necessarily of 6:1 means that the span length will be 6 times as long as the chord length. So we could have a span length of 12 meters, huge span obviously, but a chord length of 2 meters. Okay, so a 6:1 aspect ratio. So a very long thin wing is a high aspect ratio. A glider has a high aspect ratio. It needs this particular type of design because it flies very slow. Looking at the lift formula, you can see that if we have a very slow speed, what we need to do is balance the lift force to equal the weight with something else on the actual aircraft or on the glider, and what we can do is increase the coefficient of lift, which means a high angle of attack. Obviously that will then give us a greater pressure differential on the wings, which will then produce more induced drag. So in order to alleviate or reduce that induced drag, a high aspect ratio wing is produced, and that's the reason why gliders have this particular design feature. They're very slow, obviously, not as fast as commercial airliners. So therefore they would produce high amounts of induced drag if they had normal wings, normal rectangular wings. Last on our tutorial we talked a little bit about the stability of the aircraft, the longitudinal and the lateral. I'd just like to go through that particular part of the chapter of that issue again, just so that we have that focused in on our head. So, longitudinal axis, or the axes of the aircraft, the longitudinal axis along the aircraft. Lateral axis from wingtip to wingtip, and a normal axis is going through a normal or vertical axis, as it may be called, and they all pass through the aircraft's centre of gravity. all at the same point. So what happens with these particular axes? Now we talk about stability about the axis or around the axis. Imagine a rod going through the longitudinal part of the aircraft. We would then, in order to rotate around the longitudinal axis, we are producing a rolling moment. Okay, and this will give a lateral stability. So longitudinal axis, lateral stability is about the longitudinal axis. The lateral axis then, as we've said, moving about the lateral axis, we are in pitch. So the aircraft is either going to be climbing or it's going to be descending when it's moving about the lateral axis. And that, in order for it to be stable, is longitudinal stability about the lateral axis. The last one we talk about is directional stability, and that is through the vertical or normal axis. And that gives us the movement in yaw. The design features, in order to reduce or stabilize the aircraft, remember stability is all about stabilizing the aircraft without pilot intervention. So the aircraft will do this automatically. The pilot has no input to this. As such, the stability of the aircraft. Starting off from directional stability, it's about yawing, and it is the vertical stabilizer, the fin, which acts as the directional stability medium about the normal axis. About the lateral axis, the longitudinal stability, we have the horizontal stabilizer, the tailplane. And necessarily for the lateral stability about longitudinal axis, okay, rolling motion, there are 2 or 3 different design features on the aircraft. One of them is dihedral, which allows the aircraft to move out and upwards. Other design features can be high wing and high fin. Also, sweep back, or the sweep back of the wings on most modern aircraft now gives a stability, lateral stability about the longitudinal axis. A couple of other features on aircraft which sometimes we don't always sort of see on a lot of the modern aircraft, what's called ruddervators. They are the rudders and the elevators together, and they give a pitch and yaw movement. So ruddervators give a pitch and yaw movement. Can either be controlled independently or both together, depending on the type of control that the pilot would like. The other design feature that we see with this, where they either work independently or together, are what's called elevons. And they give a pitch and roll. They are elevators and ailerons combined together. Again, either independently or will move both together, depending on which control movement the pilot is inputting at the time. One last thing I'd like to go over would be the different tabs that are used on the actual aircraft. This can sometimes cause a bit of confusion, especially when questions are asked if one wing is, if an aircraft is flying low on the left wing, whereabouts would the aileron trim tab be? Well, that is all about, remember, trim tabs normally, especially on the aileron, will act in the opposite direction to the actual main control. So if the aileron, if the wing is flying low, what would happen is that the aileron would be up, giving the aircraft a low. That's why the wing is flying low. So therefore, the aileron trim tab would be down. Towards on the elevators, we have different types of tab. Just going through the ones that are in the book or on the actual Moodle platform. The balance tab. Now, the balance tab assists the pilot to move the control, and it moves in the opposite direction to the actual control surface. So the balance tab assists the pilot moving in the opposite direction to the control surface it is attached to, or it is meant to assist in moving. The servo tab as such is connected to the flight deck, directly to the flight deck, and it is pilot inputted. This then allows the pilot to only move the servo tab rather than moving the whole control surface itself. So therefore the servo tab will move the control surface, and the pilot moves the servo tab. So the servo tab is connected directly to the flight deck. Another one which may come about, anti-servo tab. Now this in actual fact places the control column back to the neutral position, assists the pilot to place it back to the neutral position. We also have anti-balance tabs. The anti-balance tab gives a pilot a feel, like an artificial feel, to the actual control surface that he's trying to move. This allows a certain control or feel, as I say, about the control surface to stop overstressing of the actual aircraft. And one last one, which we've got in the actual module notes, are what's called spring tabs. And they are used when high aerodynamic loads are being encountered and the control column or the control surface needs to be moved. This will, in actual fact, help the pilot move this control surface under high aerodynamic loads. Only comes into effect at those high aerodynamic loads. Under normal loads, it will move with the actual control column it's connected to. Okay, I think that's about it for the online tutorial. Good luck with the exam on Friday. As I said, 20 questions, 25 minutes. Read the question and look at the answers. So just remember, maybe write the lift and the drag formula down, just to give you a heads up when questions do arise about those particular types of factors. Okay, good luck with it, and see you later.